I think we're only going to have probably, I'm hoping only one more video before we take a break here for you guys. So basically the last one, all we did was drop in two things and we talked for 10 minutes about it. But this one is going to be a little bit more stuff that we're dropping in. And I think you'll find that it's actually pretty easy to understand. So the objective here, we have lines. We have an intersection line that we're going to need to map to measure the length. So let's do something real quick. If you look at what we have on the output, we have curves, and we have, I think it's points. So that's the intersection points at the end of the surface. Those are going to come out in pairs. But basically, what we need to do is analyze the length of that curve. So if we've been working a lot with surface analysis, but what you should be aware of is that there's also a segment under curve tab. There's a panel also called analysis. So just like you can extrapolate all the information like area, volume of solids, you can get length, locations, and stuff off of curves that you've created. So in this case, we're going to go under analysis and pull in length. And it's asking specifically for a curve. Otherwise, you can't measure a length because a point has no length. So we plug in the curves. So these curves, something to note, they're coming out in sets. So when you see that dashed line, remember it's coming out in a set, right? So each curve is packaged in its own set of data in a particular order. And that's noteworthy. But what I'm going to do here is drop in a panel so we can visually see what information we have. So if I pull this one down, you can see that we've got lengths that are anywhere from, I see 29 to 150-ish. Or, oh, there's a 250 in there. So those would be the lengths of every single panel that we have on the building. And if you went through and you counted them, or if you just hovered over the L, it tells you that there are 16 of them. That's good. That means it matches the number of faces that we have on the building. Move this down a little. Collapse this, but I'm going to leave it up so you can still visually understand what we have there. And so here's really the kicker. We're going to create groups of faces based off of the lengths that we have in that list. So here's a good way to measure your minimum and maximum value. Remember, do you recall what the term is for something that has a minimum and maximum? Close. You're right, but yeah, there's another term. Yes, domain is what I'm looking for. So domain, we can find domain. No, I'm sorry. We want bounds. So what bounds is going to do is it's going to give us the minimum and maximum value of a list of numbers. So I plug that in, and what I get, oh, you know what? I need that to be flattened. Sorry. So see how it's coming through in packages? And because each set of data only has one item, that means that for the first set, the minimum value is 51 and the maximum value is 51 because there's only one. Now when you flatten that, you get this that reads, well, the output actually, or the input is now going to read as an individual list of all of those lengths. And then it's going to give you the lower value of 24 and the upper value of 249. So why are we doing that?
To make different instances for different lengths.
Right. Now we can subdivide based on that minimum and maximum value and then create sublists that are going to basically give us what we need. It's going to give us a list of the items that we want to isolate. So let's take a look at Flattened sets list. So extract subset of a list. I actually kind of forget which one specifically we want. So I know we want to partition a list into sublists. Size of partitions. Ah, that's what I'm looking for. So I'm going to unflatten that, and I'm going to flatten this one. So there are a couple of things I'm going to do here. I am going to reorder the lists, or I'm going to reorder the list so that it reads from top to bottom, I think. And then list. I'm blanking on what I did in the past. Ah, there we go, sort list. There. That's what we wanted. So if you drop in sort list, it's under set list, sort list. I'll group that. Set list. And it's called sort. So what that actually gave us, and I'm going to do another panel so now you can see the difference, is a list that's actually functioning in terms of minimum to maximum value in that direction. Does that make sense? So now we can partition that list into subdivisions that's based on, you know, the highest numbers or the lowest numbers. Okay, so I'm going to feed that list in. And then we have 2s and 3s. 3, 2, 3, 2. So the way that this is packaging it for the partition is when it says the size of the partitions, it's a maximum number of index values that are going to be in that set. Does that make sense? So rather than the size of the partition actually saying, well, I want to split it 3 times, this one is actually going to be a maximum number that's going to define the list. So for us, we can do a numerical relationship if we want it to be a divisor. So this is what I'm going to do. Now we're getting kind of complex here, so I don't expect you to get this the first time around. I'll walk you through it, then I'll have you do it again on your own so you can understand. But basically, I'll pull that out. Rather than saying manually, I know I have, right now, I only have 16 numbers. But when I plug in every single building, those 16 numbers are going to be, you know, probably 1,600 numbers. So I want this to be automated so that instead of changing the number later, it just automatically changes based on how many inputs there are. So that basically means I have a list that has 16 numbers. I can measure under set list. It's this cool one called list length. I can measure and get a number that just tells me how many items populate that list. Then I can do something pretty clever with math. And I can divide that number. So I go up to operators, division, like that. And I put in, I'm going to do it with a panel so you can visually see it all the time. Divide it by 2, 4. I'll divide it by 4. And that gives me the number 4. So 16 divided by 4 is 4. And then we plug that into the list, and so our subdivision is actually going to come out in packages of 4. So now our next panel, so that you can see the progression, put it up here so you can kind of see it this way. Gives us that same list of numbers, but in groups. So we just did a lot, right? We did a lot of restructuring of data. Okay, what we were given here, back when we measured the length of each of those lines, the curves, we were given a list of a whole bunch of numbers. We are going to use this later. I'm going to leave it there. I think we're going to use it later. But then we kind of went a different direction, and instead I decided, well, rather than dealing with a boundary for now, I'm going to use the reordering or the sort, and then I'm going to partition that sorted list into individual items.
And sort is it's going to do everything. It's going to order everything based on what. Right there, it went from at the top, the lowest value, to the highest.
Mm-hmm.
Is it always going to do that?
Unless you change it, you could do well. For the most part, yeah. I mean, there are a whole bunch of operators you can do to a list. So, for instance, if we go under set list, and I'm just going to show you a few, you can just split it in half. I guess you could just split it. Actually, in fact, that might serve us better.
Split what?
It just splits the list. Let me play around with that for a second. So the list here, right, if we have our raw data, it comes in as a bunch of numbers like that. So if I pull the list in like this, the index, let's see if we can just split it 4 times. I think this is how this one works. Ah. And then B gives me the other side. So guys, I'm just trying to think through what the most streamlined way of doing this is going to be. So this one is just going to, split it into 2 ways. It just breaks it at a certain point that you've defined. We have reverse list. We can partition it, which we just did. We can get a sub list, which if I look at what it wants the list, it wants a domain. So actually that might work out for us too. That's probably good. Let me see something. Divide domain. Ooh, wait, that's what I want. I'm sorry. This is what I think I want. So I do want to use the domain. I'm going to group this and keep it. I'm going to put it to the side. Sorry guys, I think I led you down a rabbit hole here. Yeah, I did. I'm pretty sure. So I think what I want is to divide the raw list here. Divide it by a domain, I think. Because, I'm thinking ahead, right? So what's going to happen, and this is where lists become really, really important. Okay, and this video is getting really long, but this is going to be troublesome. What's going to happen is, I have a list of raw data that comes through indexed. Right, so this list of raw data is indexed. So it says 0, 1, 2, 3, so on and so forth. But when I reorder it, and it has a numerical relationship, and I say, well, I want this group 1 to only have 1 subdivision. Well, the problem is I can't make that list now communicate back to the surfaces in their original position. Nor can I reorder that list by an external optional sort. So I can't say I want to reorder that list the same way I reordered this list, because this list is reordering based on numbers. Oh wait, synchronously. Ooh, wait. Ooh, wait.
So in other words, once you've categorized information, you can't do it a different way.
You can. my knowledge is limited on the subject. So if it's doing it synchronously, maybe we can reorder the surfaces. I want to do something real quick. I want to test something with you guys. So this is me. Now I'm just exploring because this is kind of new to me. I didn't think you could do this before, but I just read this a little bit more closely. It says optional list of values to sort synchronously, which means that maybe if I plug in the faces, the list of faces that I'm analyzing, it'll reorder the faces as well. And the reason I think that that's a possibility is because it says empty generic data parameter, which means it can read anything. It can read booleans, which are lists of zeros and ones or trues and falses. It can read geometry. It can read numbers. So I'm going to try that out real fast, but I have to do it in a way that I can test that it's been done correctly, because a surface is a surface is a surface. If I pass it through and it reorders it, I can't tell. But if I analyze the area of each of the surfaces, which is dependent upon the length, then I'll be able to measure and see that it has actually ordered it properly. So let's do that. So I've got curve lengths, curves, and these are my individual surfaces. So I'm going to do another surface analysis. And this is, sorry, this is going to be a long video, guys, but it'll help. Analysis area. So here are my two raw data inputs. So I've got under index 0, the surface that is 51 feet wide has an area of 2311. The surface that is 29 feet wide has an area of 1326. So if this reorders it so that 1326 is at the top of the list, and wherever 51 falls in the list, and it just goes by size, then it works properly. So what I'm going to do here is basically take all of the surfaces that are feeding in, and I'm going to plug it down in to sort synchronously. So, oh, sorry, I need to analyze those as well. So this gives me, see, it still has 16 surfaces. If I plug those 16 surfaces into G, and I look at the area, well, there it is. So looks like that is going to be a more seamless approach. Does that make sense? Huh? No, it doesn't? So let me get rid of all the rabble. I'm going to work backwards here. I'm going to get rid of all the rabble. I almost led you down a rabbit hole with all of this. So I'm going to get rid of that, that. And then you and I, like all of us, will redo this together. But oops. Don't need that. Don't need that. Well, actually, I do need those. I'm going to use those. So here were our possibilities. Yeah. Well, I'll keep that. So here are our possibilities, right? We have surfaces, and I'm going to pull those out like this. And then we have the curves that they created. Okay, so the surface, I analyze the surface length. Go back here. This is all back at the beginning. Every single poly surface has been broken down into individual surfaces. Okay, so this is raw data, individual surfaces. I am trying to measure the length of those surfaces and then organize them such that I can manipulate them later on in a synchronous way, now that I have that cool word in my vocabulary here. So I went all the way down here, and now I say I've got this list of lengths that I analyze. And I want to, I'm going to use those to identify certain ones based on a boundary that says, you know, my smallest surfaces are going to be manipulated in a certain way. My largest surfaces are going to be manipulated in a different way. So to do that, I have to restructure the data and reorder it so that it is a way that I can subdivide it like that. So I used, down here, I used sort. So this sorts it into information that I can then break down into groups of, you know, smallest to largest. That part you get, right? Okay, you might not know how to repeat it immediately, but you get it. And then the challenge I was having is that I was trying to figure out, well, if that's true, how do I take the actual list of surfaces, which are these, and make sure that they get reordered as well? Because when I try to remap, so if I take a remapping of, where's the original one? You know, index 0 is, call it length 2. And I say I want length 1, which is this one, right there. I want length 1, the smallest one, to only have one subdivision. Right now it lives at index 2, or index 1, sorry. But once I've reordered the lengths themselves to break them down into groups, then the smallest one is going to map to index 0 because it's at the top of the list. So when I redo the way that it's mapping, it's going to take this one, which is supposed to be a length of 2 and have 2 subdivisions, and it's going to give it only 1. It's difficult to understand, but what, I mean, if you just look at the data, and if you look at this next to that, you can kind of see.
But I mean, how's it going to do that by just throwing a list on?
It's, well, I'm gonna make it do it later.
You're going to break down the list, like, okay, 1 through, or 0 through 5, these are my smallest ones are going to have 1, then 6 through 10 are going to have 2.
Mm-hmm.
With that list?
Yep.
That would be making I forget the word, subsets?
Sublist, or a set.
Oh, sets of information.
Yeah.
And you can do even something like for every wall that's between 24 and 61 feet, it gets this many subtractions.
Yep. That's true. Yeah. So you could do stuff like isolating parts of this. So say I want my 5 smallest surfaces to only get 1 subdivision. And we're gonna, this video is like incredibly long, but we're gonna move on and I'll show you how to actually do that here in just a second. But quick recap again. What we added in, and let me, well, it's kind of hard to isolate this, but I'm going to use this in a bit. But basically all we did was take those surfaces, grab the area, and plugged it into sort. So this stuff we don't need. And this is just analytical, and right now that's just analytical. So this is essentially all we actually did right now. We grabbed the length of those curves that we isolated, we resorted them so that they go in order, and then we took the surfaces themselves and we synchronously reordered those as well. And I checked it to make sure by analyzing the area of those surfaces. Okay, let me stop this. This is madness.